Hello, Calc students. This is Mr. Beck. Today we're going to be talking about a lot of different sections. First one that we're going to tackle is going to be volumes by cross sections. So one of the things when it comes to volumes by cross sections, I'm going to open up a GeoGebra link here for you. When it comes to volumes by cross sections, the idea behind the cross sections is what happens if we have a geometrical shape. That geometrical shape is, if you look at that geometrical shape, you take the cross sections of it, they're all the exact same shape. So you can see a really weird looking function in here. There is only one cross section that is showing right now, or there's only one shape that's showing right now. But if we cut it out into smaller and smaller portions, what you can see is it's a changing shape that's going to fit the curve that's in the XY plane, and the one that fits the curve in the XY plane. If we take cross sections of each one of those, you have the same shape. In this case, it's going to be an equilateral triangle. Let me go ahead and change the shape. Isosceles right triangles. So if you look to the side, you can see that all of these are isosceles right triangles. From the top-down view, we can see that the shape is still in the XY plane inside the curves that are there. But if we look at the side, we can see a little bit more of the dimensions. We can see how each shape really is a equilateral triangle or isosceles right triangle. We could do squares, same kind of thing. The squares all fit in the XY plane. Regular pentagons, this one's kind of like the fun one to look at because I would never think to do regular pentagons, but we definitely could if we really wanted to. One of the common ones is going to be semicircles. So these are the kind of shapes we're going to be looking at. And just like before, when we were talking about anything geometric, being able to visualize what's going on is going to be the key. So when we go back to looking at volumes by cross sections, one of the things that we first want to do, or at least I encourage you to do, is draw a shape of the graph that's in the XY plane. So the shape of the graph that's in the XY plane, you see right here, I just highlighted it. Now, then we want to say, okay, our cross sections, are they going to be perpendicular to the x-axis or perpendicular to the y-axis? So something to really focus on. Cross sections in this case are going to be perpendicular to the x-axis, and that shape is a square. So I sort of have that visualized right here, where perpendicular to the x-axis we have squares, and you can see the different shades of colors there. Now, when we draw this shape, and really to begin with this, we draw our shape in the xy plane, that's what I highlighted there before. We're going perpendicular to the square. Why this is perpendicular to the x-axis? Why this is very, very important is because the thickness of that representative rectangle is going to be dx. I know I've been talking about this representative rectangle for a while. Today it's going to come into play quite a bit. So this is a distance, and if you remember last time, I said it over and over again, distance is always measured as top minus bottom or left minus right. So if we have the equation of the top half of the curve, which is the positive square root, and the equation of the bottom half of the curve, which is the negative square root, then when we take top minus bottom, we can simplify that expression to what I have here. Now, big thing to match up is I said that each cross section is a square. So the side that's in the XY plane has to match up to the side of a geometric shape. Now, kind of like what we did before when we rotated, we took the sum of all of these circles and we added all these circles together, and that's where integration kicked in. So what we're going to do is we're going to take the sum of all the circular areas. In this case, we're going to take the sum of all the square areas. So I need to know what's the area of the square. The area of the square as a function of, or is s squared, but as a function of x is listed right here. Hopefully you can see the math and work in math. But then to find the volume that gets created, we are going to sum all of the squares going from the x value of -2 all the way to the x value of +2. So that's where the integral comes in. A sum from -2 to +2 of all the areas. Now, what's the thickness of every single one of these squares? The thickness is that differential of x. So then translated is 4 times 4 minus x squared dx. Now, what I did was, because there is so much going on today, normally if this was a standard class, I would have students work these problems on their own. But because this is not quite the standard class, I'm going to have the students do a lot of the calculations in their calculator. So the integral from -2 to +2, and then 4 times 4 minus x squared. Wow, definitely did not put that in there like I thought I did. So for, struggling here today, guys, bear with me. So for parentheses, 4 minus x squared dx, and we should end up with 128 over 3. A lot of these we could do by hand. We are just not going to do them by hand just for the sake of time. Next problem, we now have the region as x squared plus y squared equals 9. So if you see the very first thing that I did in my problem, I drew out that circular shape, and I know that the radius of that circle is 3. So that's 3, that's negative 3. So we're going to find the volume of the solid where each base by cross section is an equilateral triangle. So what we're sort of seeing here, is each one of these shapes is an equilateral triangle. So the next question is, what is the area of an equilateral triangle? The area of the equilateral triangle, if we use Heron's formula, is the square root of 3 over 4 side squared. So that side is what's going to be matching up in the circle that's on the xy plane. So what's the length of that circle? We could do the same thing that we did before. We have both the positive and the square root of negative square root of 9 minus x squared. So when we subtract those two, we are going to get the distance in the xy plane. Something to kind of point out, when x is 0, we should have a distance of 3, and that is true because that is 2 times the square root of 9 minus, I guess the distance is 6. 2 times the square root of 9 minus 0, where we have 3 up and 3 down. When x is negative 3, we should have a distance of 0 because that's 2 times the square root of 9 minus 9. When x is, say, maybe 1-ish, which is what that is, we should have a distance of 2 times the square root of 8, or 4 times the square root of 2. Anyway, that distance is represented, that's a varying distance. And so when we do our integral, what we're saying is it's going to be the sum of all these varying distances. And by plugging in the different x values, we're actually able to see each of the distances come to play. So anyway, back to the problem. Our area formula in terms of x, you can see that written right here. And if you notice, I simplified that expression. And then to find our volume, it's going to be the sum from negative 3 to positive 3 of that area formula dx. And if we throw that in the calculator, we should get 36 over 3. Let me go ahead and throw that into the calculator. Remember, shortcut key, shift plus, integral from negative 3 to positive 3. And then I'm going to do the square root. Something that I was about to point out is this is a perfect example of an even function. And don't forget, with even functions, we can multiply by 2 and just go from 0 to 3. And dx, 36 square root of 3. We're in good shape. Problem 3. So when it comes to problem 3 here, we're going a semicircle perpendicular to the x-axis. Our semicircle perpendicular to the x-axis, if we draw our shape, x equals y squared, which looks like so. What I have in green is going to be my representative rectangle. The thickness of that rectangle is dx, which means you have to put everything in x. And I know I'm going perpendicular to the x-axis. Well, that s translated to a semicircle means that this distance right here is s. Now that distance is a diameter, and for the area of a semicircle, the area of a semicircle is 1/2 pi r squared. So we have to cut that s in two, like so, so we can have the sum of, or we could have one of those semicircles added. And you put all that in terms of s, we have to find the distance. So kind of like before, we have the positive square root of x minus the negative square root of x to give us a distance length of 2 square root of x. So our area is going to be 1/2 pi times square root of, I guess I was just jumping up there. If you notice, I simplified that expression to 1/8 pi s squared. So when I put the s in here, I now have 1/2 pi x. So my volume is going to be the integral. Notice how the integral goes from 0 to 9. That's because the beginning x value is 0, the ending x value is 9. So the integral from 0 to 9 of my area in terms of x dx. And then this one I integrated by hand. I got 81 pi over 4. This is going to be the first time we're going to go perpendicular to the y-axis. So if we're perpendicular to the y-axis, that thickness is dy. That means we can use this equation, x equals y squared. So that distance, what you can see here, now it's a horizontal distance. And if you remember, distances are measured right minus left. So this is the x value of 9 right here. And then we're going to subtract the left side, which is going to be on the curve, which is y squared. So that s distance is 9 minus y squared. Now, what shape are each one of these cross sections? The shape is a square. And just like before, the area of a square is s squared. So if we put that side length squared in, we now have our area as a function of y. Our volume is going to be from this y value of -3 to this y value of +3 of side squared, so the area dy. Now, once again, this is another perfect example of an even function, which we could take double from 0 to 3 if we were going to do this manually. We could throw it in the calculator, and we will get one of those two answers. For example, number 4, what I have here is, once again, I have a shape. Now, this is kind of like a tilted view, and this tilted view, usually what happens is this is the x-axis and this is the y-axis, and then this is the z-axis. You could do a lot of different orientations, and it really just depends on whether you're doing a right hand or a left hand. And for those people who know what I'm talking about, okay. If you don't worry about it. So what I did was I drew my bounded region. So for y plus 3x equals 12, which translates to this equation, x equals -4/3 y plus 4. That means my x-intercept is 4. Then my run is -4 and my rise is 3. That's how we graph it with respect to y. Anyway, we're going perpendicular to the y-axis, and each shape is a semicircle. So one more time, the area of a semicircle is 1/2 pi radius squared. And remember, the radius is going to be half of that distance that is in the xy plane. So that distance in the xy plane is going to be the -4/3 y plus 4 minus 0. So that's our overall distance. And then 1/2 turns into the 1/8 pi s squared, which is what we had before. And then throw it in the calculator, we are going to get 2 pi. Just remember, this is our area formula. That area formula is going to be based off of whatever the variable is we're working with. This is going to be the thickness, and we are summing all of those areas to create an overall volume. For part B, now that region is an isosceles right triangle with one leg in the xy plane. So if we have one leg in the xy plane, this distance is also s, and so the area is 1/2 s squared. Well, s is the exact same value as before. So we are going to sum all of the areas times their thickness, and we will get 8. We could do this by calculator, we could do this by hand. As I said last time, we did a lot of this by calculator just because there's a lot of work to do today. Some big difference you might see, what happens if you have an isosceles triangle with the hypotenuse in the plane. So this is a common one, where this is now S. So if you remember our 45, 45, 90 triangles, we divide by the square root of 2 to get the side length of the equilateral, and then the area is going to be 1/2, and then each of those legs squared, which simplifies to 1/4 s squared. So that would have been the different area formula that would plug in here if the hypotenuse was in the xy plane as opposed to the y. Example number 5, we have a solid that has its base and has as its base a circular region bounded by x squared plus y squared equals a squared. Now, when it comes to this is a circle with a radius of a, and we're going perpendicular to the y-axis, which is why I solved that equation for x. This is the positive half of the circle, the positive square root. This is the negative square root. So our distance is going to be the positive square root minus the negative square root, or simplified here. Because this is a square, the area is going to be side squared. And then that gives me this expression. And this is another one that I just threw into the calculator. We should be able to do this one by hand as well, but in the calculator, you actually are able to do this in terms of variables. So let me show you this one. So if I take shift plus, I'm going to go from -a to +a. And then my area function is 4 a squared minus y squared, then dy. You'll see it's 16a cubed over 3. So you are allowed to put variables in here as long as those variables are not defined. And we know they're not defined because if you take a look at this variable, it is not bolded. It is just italicized. What happens in this case, the isosceles triangle, the base is in the xy plane. The altitude is equal to the length of the base, so both of those are s's. Therefore, this is just 1/2 s squared. So if you notice, I kind of cheated here because if this one is s squared, this area is s squared, this one is 1/2 s squared. All I did was just took half of the volume that we found before because we were summing up half of the areas that we had before. Moving right along. Then we get to the shell method. And I'm waiting for, there we go, it kicks in. The shell method. If you remember, we did volumes by disk and washer, and I have a link on this page. We also had volumes by cross-sectional area. When it comes to the shell method, I'm going to point out the idea behind the shell method. The idea behind the shell method is we are going to take volumes, did not mean to do that, we're going to take volumes by rotating regions around an axis. And you're like, wait a second. I'm like, yes, we did that before. So take our volumes. I did not mean to do that. Let's reset. Okay, so what's going to happen is we are now going to revolve our representative rectangle, but we're going to revolve it around an axis parallel to that representative rectangle. And if you notice, what this creates is a cylinder. Then what's going to happen in the cylinder is we're going to say, okay, the volume of the cylinder is in essence going to be the surface area times the thickness. Now this is a much simplified version, but the volume of the cylinder is going to be surface area times its thickness. And if you think about it, it's kind of like it's a good representation that if we want the entire thing, the thickness is going to be the radius. But this thickness is going to be just dx or dy. In this case, it's going to be dx based off of the perpendicular to the x-axis. So going back to the formulas that we see here, our volume is going to be 2 pi RH, which is the surface area of a cylinder, and then times the width, which is going to be its thickness, and that thickness is going to either be dy or dx based off of which variable we're using. So once again, you can see 2 pi RH and then times our thickness. So one of those shells. And then we are going to sum up all of those shells together. And we're going to sum up from the different radii. So really, if you think about the shape that I have here, this triangle, which does form that region down there, the radius of each one of these shells, radius of each one of these little cylinders is going to be this varying distance. So now radius is a varying distance. Height is also going to be a varying distance. So we're going to have to look at both a vertical distance and a horizontal distance at the actual same time. Now we want those distances to be with respect to the same variable, and we know what variable that is based off of the delta x or delta y that comes from the rectangle. So the vertical distance is going to be that changing y value. In this case, it is just y minus most likely 0 if that's our axis revolution. So our vertical distance is just going to be y, and that one in terms of y. Our horizontal distance is going to be our function with respect to y minus 0. So our function minus 0. Let's actually put that into play. What you can see here, I kind of represented it. Our vertical distance, remember, is always going to be top minus bottom, which in this case is going to be the y distance minus whatever the axis is. Our horizontal distance is always right minus left, which is going to usually be the function, and then in this minus where we begin, which in this case is most likely 0. We can do that vertically. If we have a vertical representation, that means it's with respect to x. So this distance is going to be that x distance from 0. And then, so as you can see, it's x minus 0. Our vertical distance is going to be our function height minus 0, assuming this is y equals 0 as well. And so 2 pi RH, and then times the thickness. Now what you can see on this graph right here, I tried to give a visual representation of what this looks like when it got revolved. This is actually why we have to use the shell method. Because if we wanted to do a horizontal representative rectangle, we end up saying the outer radius is this function and the inner radius is this function, which you're not actually able to do. So there is a reason why we teach you the shell method, because a function which is not one-to-one and you're revolving it, it's going to have a repeated function that we're not going to be able to see all of our values properly. So that's why we have to use the shell method. So we start off by saying our overall surface area of a cylinder is 2 pi RH. So what's our radius? Our radius is going to be the varying representative rectangle that we see right here. So it's going to be that varying whatever the x value is minus, in this case, 0, which you can see that I have here. It's the x value minus 0. The vertical distance is going to be our function's height minus 0, which comes from right here. The 2 pi RH is the surface area of the cylinder. And then we multiply that by its thickness and sum up all of those. And once again, I use the calculator on this, 2 pi RH, to come up with the value. On example number 2, we already have our function in terms of y, like so. So in this case, I have a horizontal representative rectangle, which is what we see right here. So that horizontal representative rectangle, which means the thickness is y. So we have to put all of this in terms of y. And that makes sense because we're going around this axis of revolution. So with that said, what is our vertical distance? It's going to be that varying y value, minus 0. Our horizontal distance is going to be our function height, minus 0, because it's right minus left. So 2 pi r h, and then 2 pi r h, which I have right here, times the thickness is, and we sum it up. Now this one I actually did by hand because this one's not too bad to do, and just as a little bit of fun, don't forget that this is a chain rule. So this is a UDU, which then gave me that integration and then simplified answer. What I like about this problem is really a comparison between doing this either by the shell method or by the disc and washer method. This is what we did at the end of last time's notes. So the bottom half of this, if we do disc and washer method, so this is a disc revolved, top half is a washer revolved. And then if we do all of the integration, we get 3 pi over 2. Doing this by the shell method, we now see that this horizontal radius is just x minus 0. This vertical height is going to be function minus 0. And so 2 pi r h. And I did this one manually, and I got the same overall volume of 3 pi over 2. For example number 4, this time we're revolving around a different axis. We're revolving around x equals 2. So if we're revolving around x equals 2, the biggest change is our radius is now going to be 2 minus x. And the reason why it's 2 minus x is because this varying x distance is still going to be the distance from here to here. But we always go right minus left, so 2 minus x is going to be my radius. Then the function height is going to be whatever this function height is. And if you notice, this is capped off at y equals 1. So our top minus bottom is going to be our function minus 1. So our radius, as I mentioned before, is 2 minus x. If we take our function minus 1, it's just x cubed plus x. And we can throw this into the calculator, and we will get 29 pi over 2. Could you do this by hand? Absolutely. For example number 5. On example number 5, we have just the graph. I have a bunch of examples in here just to show you different ways of looking at it. It's all of these are going to be 2 pi RH. So do you remember how to graph that as a parabola? And if you see, I have it kind of like written in that, although that doesn't look very well, very nice. we're going around y equals -1. This is a perfect case where we want to use the shell method. So we have our radius as y minus -1. Again, that's kind of hard to see with the colors that I have there. So y minus -1, or y plus 1 is my radius. My height is going to be function minus 0, which is what I have here. Throw it in the calculator. This is a shape that 4 minus e to the x, you can see the graph written right there. So if we're going about x equals 3, do we want to do this horizontally with a disc and washer? Do we want to do this vertically with the shell method? I chose to do the shell method just because it's a little bit more straightforward. So our radius, because the axis is to the right and the rectangle is to the left, is going to be 3 minus x. That's my radius. Now, one of the things that I needed to do is figure out what is my intersection point, which I have here. So I'm integrating 2 pi RH from 0 to the natural log of 4. And as I said, I threw that in the calculator. I have both an exact or decimal approximation, and this is our exact answer, which is kind of nice. Example number 7, very, very similar. Just trying to get you to see what e to the negative x squared looks like. So 2 pi radius is x minus 0, height is function minus 0, boom, boom. Example number 8, we do have to find our 2 intersection points first. So where do these 2 functions intersect each other? I did this graphically by putting them both into vertex form, going from 2 to 4. So 2 pi from 2 to 4. Let me undo those again. The radius, in this case, if we're revolving around x equals 1, which is going to be that axis, right minus left is going to be whatever that x distance is, and then minus the axis of 1. So let me see if I can, there we go, highlight it again. And then the height is going to be the upper function with respect to x minus the lower function with respect to x. Kind of nasty looking on one sense, but ends up being a beautiful answer. For example, number 9, I have that graphed. Doing this with the shell method. Our radius, because we're going around x equals 3, our radius is 3 minus x. And then our function height is going to be the upper function of 4 minus the lower function of 2x, 2 pi RH, 56 pi over 3. For example number 9, we have 3 different functions, the square root function here, y equals 0, and x plus y equals 3, which will be this line. And this actually, I believe, was an AP problem at one time. So you could do this by either disc or washer method, and I think the AP was looking for students to do this by the disc or washer method, but you could actually do this one by the shell method. Now our function height is going to be right minus left, which is going to be 3 minus y, and then minus the square root. And then the radius is going to be our 2 minus y that you see here. Oh, by the way, that square root we had to solve for y. Anyway, 2 pi r, and then our function height, which is the right minus left. Throw it in the calculator, 23 pi over 6. The last topic that we have to do right now is arc length. Now, this is going to be a very butchered, shortened form of what we're looking at here. But when it comes to arc length, the idea behind arc length is we're going to take each one of these sections and we're going to find the distance as segments. Now, each segment, in this case, this x value, or if you notice, we could use Pythagorean theorem to find this. So each horizontal distance is going to be x1 minus x0 in this case, or x2 minus x1, or x3 minus x2. We could simplify that by calling that delta x in terms of all of our delta x's are going to be the same. Similarly, our delta y's are all going to be the same. So our delta y's are going to be y2 minus y1 or y1 minus y0, but they're all are going to be a certain vertical. So while the x changes are going to be the exact same, the y changes most likely won't. And so we're going to have to look at this in terms of what is the x change, what is the y change. So if we make more and more of these segments, if we cut this into smaller and smaller pieces, what we can actually do is say each distance is going to be the delta x squared plus the delta y squared, or the square root of that, because Pythagorean theorem. Well, if you factor out the square root of delta x squared, you end up with this expression, which we can put it all together as the square root of delta x squared is really the absolute value of delta x. And so we'll take delta x times the square root of 1 plus slope squared. Well, slope is going to be f prime of x. And so we will integrate or find the sum of all of these distances, which is the square root of 1 plus f prime of x squared, and then times that delta x. We could do this in terms of y also. You see I did this here, where we could factor out the delta y squared. So we have delta x squared over delta y squared. Same kind of thing, but then we're going to go from the y values. So let's put it into practice. If I want to find the arc length of the graph of that function, I first need to find the derivative, which is what we see here. And then when we have our derivative, which is what we see here, we will say it's going to be on the interval from 1 to 3. So we're going to sum all of the distances of the square root of 1 plus our derivative squared times dx, which we get 92 ninths. Now, unfortunately, I skipped through all the algebra, and this one is a beautiful algebra style problem, but you end up getting 92 ninths. I'm going to pause here for just 1 second, and I'm back. Take a look at example number 2. I did this one by hand just because I like the math that's involved with this. First thing that we're going to have to do is look and say we're finding the arc length of the graph of this function. We don't actually need to know what this function looks like because we're given the equation and we know that the interval, what it's on. So first thing we need to do is find the derivative. So the derivative of the natural log function, if you remember, it's the derivative of what's inside over what's inside. And what's true about that is negative sine over cosine is negative tangent. So when we plug that into our formula, the square root of 1 plus the derivative squared. So 1 plus the derivative squared. We know that we have 1 plus tangent squared y. And our trig identity of 1 plus tangent squared is secant squared. So this is the square root of secant squared, which is just secant. I know it's the absolute value of secant, but it's secant. This is a situation where I doubled the integral from 0 to pi over 4 because secant's an even function, and then I evaluated that analytically. Last but not least, we're talking about the surface area of revolution. The idea behind the surface area of revolution is kind of similar to what we did before, where what we're going to do is we are going to take a small representative rectangle, we're going to revolve it to form what you see here as it looks like a little bit of a ring. Now I'm going to undo that and zoom out just a little bit so that when we take that ring, and I can change the color. So we're going to take that ring. When we revolve the ring, what ends up happening is we end up with, once again, that cylinder shape just like what we had before. Now, the way that we're going to approach our surface area is going to be slightly different, where we do have the hollow cylinder. And if you remember, the hollow cylinder is 2 pi rh. The radius is going to be this distance. It's that radial distance, and it's a varying radial distance. But the height, so that's our radius. Our height is actually going to be the arc length. So it's a slightly different view of this, but if we take 2 pi rh, the arc length is going to involve that differential, whether it's the dx or the dy. In this case, it would be the dx. But that's what we're going to end up summing. It's going to be the sum of a bunch of varying heights, and it's going to be the sum of a bunch of varying lengths. So thrown all together, and that's where we get these two formulas. We have 2 pi r, and then once again, the height is going to be that surface area, or that arc length, whether it's in terms of x or in terms of y. So 2 pi integral from a to b, r h. If we take a look at example number 3, our function is 4 minus the square root of 4 minus x squared, which is going to be that semicircle. We're going to go from the x value of -1 to the x value of +1. So our because we're revolving around, it says the x-axis. We know that if we go perpendicular, we have our horizontal dx. And so 2 pi times our radial distance is going to be that height right here, which is the square root of 4x minus 0, of course. And then the arc length is going to be the square root of 1 plus f prime of x squared. Now, one of the things that we could do in our calculator is we can define our functions. In this case, I'm going to say a of x, and don't forget we could use our colon equals for our defined functions. So a of x equals, I'm going to say just the square root of 4 minus x squared. Type it in. So 4 minus x squared. And then you see it's now going to be bold, where if I do 2 pi, let me get the pi on here, so 2 pi, don't forget your shift plus, 2 pi, I'm going to integrate from -1 to +1, and then now my radius is going to be a of x, and you can see that's bolded because it's a of x, and then the arc length, I could use our square root of 1 plus, and it looks like a minus, but 1 plus, and then we can do our derivative, which is shift minus. So our derivative of a of x squared, and then dx. And voila, we get to 25.1327. Now, unfortunately, we missed the beautiful algebra behind this that shows that we actually get an answer of 8 pi, which is really, really nice. And that's because we end up taking just really the square root of 4. So, number 4, our last big example. What I did was, in order to figure out what this graph looked like, I solved this for y, so it's a negative quadratic. Now, when I'm doing the arc length with respect to y, which is what we see right here, that arc length with respect to y, I did have to take the derivative, which you can see right here. So 2 pi, then the radial height is going to be the function that we have, right minus left, of course, and then our arc length, which we see right here. Throw it into the calculator, and we get this expression, which if we wanted to know an exact answer. So AP problems that we've seen about these in the past tend to be a little bit more of, do you recognize the formula? So the arc length formula is going to be the integral, again, from 0 to 2. We do need to know our derivative, so it's going to be the square root of 1 plus that derivative squared, which is why this answer B. For number 2, arc length, x prime equals, we do need to know our derivative, x prime equals 3y squared. So our arc length is going to, actually this one's a surface. So our surface is going to be 2 pi r h. So 2 pi, our radius is y cubed, and our h is going to be our arc length. Example number 3, you can see that I found the derivative, and I did have to take the surface area on this, or the arc length on this one. So it's going to be the square root of 1 plus our derivative squared. You can see all the algebra that I have here to get to our answer of 14/3. And then for our last arc length, this is going to be similar to one of the ones that we did before. This one's the natural log of secant. And so don't forget, derivative of natural log is secant tangent over secant, which reduces to just tangent. And once again, we have the square root of 1 plus tangent squared, which is secant like we saw before. And then we're integrating from 0 to b, because that's what they said. So hopefully this is helpful, and I will see you guys next time.